Hello class, this is CSE-4600, Section 1, Week 3, Spring 2025. Alright, so you probably got the memo by now that we are switching to a hybrid schedule. So the idea is this. We'll talk about the lecture material on Tuesday, and then I'll post a video that's basically a continuation of that, either Thursday or Friday, depending on the timing. Okay? So, for this first video for the class, it's going to be a continuation of what we had talked about last Tuesday. So, it's gonna be a summary of everything we talked about on Tuesday. So, this week was processes and threads. I'll quickly summarize processes and then we'll start talking about threads. Okay? Okay. Oh, and yeah, and the Thursday Zoom meeting, that is on office hours. So if you need help with anything, you can just hop in, ask questions, and I can help you out with whatever problems you might have, even if it's like debugging. Okay? Okay. So here's a summary of what we talked about this last Tuesday, and that is a process. This is the most central concept of any operating system. A process is an abstraction of a running program. So it's through a process that the computer can concurrently run multiple things, or even fake the ability to do that. So your computer is probably running multiple things, even right now. Even my system's running multiple things. I have like Opera GX, OBS, Unity, PowerPoint, Visual Studio, Paint.net, File Explorer, and Google Chrome. Yeah, I'm running two different. I am running two different browsers right now. Sometimes I'll even have Microsoft Edge, so it's like 3 different browsers all at once. It's a little weird like that. But anyway, the point is, your computer is able to run multiple programs at once. Some embedded systems, for example, some systems might not be able to do that. They can only ever run one specialized program. But the point is, most, if not all, personal computers can run multiple programs at once. On your system, the CPU switches between processes quickly, running them for maybe a few tens of milliseconds at a time. And because of that, it provides the illusion that multiple programs are running at once. If there is only one CPU core, this is called pseudo-parallelism. This is in contrast to true parallelism, which is achieved on a multi-processor system. Basically, there are multiple CPU cores. One process per CPU core can run. It's not uncommon to see 8-core CPUs these days. For a while, the max has been 4 cores. But yeah, my point is this. We can run multiple processes on a multi-core CPU, but even if a system can only run one process at a time because there's only one CPU core, we can fake running multiple processes at once by just running one at a time and just switching between the two really quick. So in the process model, all the software on a computer, sometimes including the OS, is organized into processes. A process is an instance of an executing program. This includes the current variables of the program counter, whatever variables are there in the program, and whatever values are in the registers. Think about it like this. When a process is selected to run on the CPU, the values stored in this virtual CPU are loaded into the physical CPU. And when the CPU decides to run another process, those values are saved in the process, and another process is loaded onto the CPU. Those register values are loaded into the physical CPU, and then it's time for that process to run. So this rapid switching is called multi-programming. Here we have 4 programs loaded into memory. There's only one program counter available. So once again, one process is active at a time, but the CPU is not only able to switch between these processes, it's able to save the state of each process. Because remember, there is a virtual CPU for each process. Any values stored on that virtual CPU is saved. So when it's time for a process to run again, those saved values are basically reloaded. It's like a save state for a game. So, everything we're gonna talk about assumes a single core CPU. Multi-core systems are its own discussion. So, with the CPU switching between processes, one thing to note is the rate at which a process performs its computation will not be uniform and probably not reproducible. So we don't make assumptions about timing. Processes must not be programmed with built-in assumptions about timing, though there are a few exceptions such as synchronizing audio and video. An analogy that the author talks about process versus program. Baking a cake is a sequence of steps that is outlined in, say, a cookbook. If you are following those steps, that is a process of baking a cake. So that's why it's called a process. It is, if you're following the instructions for baking a cake, you are in the process of making a cake. If you are interrupted at any point in that process, what you do is you save, you take a mental note of what you were doing, do something else, and then come back so you don't have to restart. The point about a process is this: the ability to save your current work and come back to it at a later time, so you don't have to start over. The author mentions what happens if your child runs in with a bee sting on his finger in the middle of baking a cake. What you do, or at least the expected answer, is you stop what you're doing and administer first aid. When you come back to your cake, you don't have to start over. You just pick up right where you had left off. A process, think of a process as an activity, something that can be interrupted by something else, but you can return to it at any later point. And this is what makes saving a process's state crucial. Additionally, the recipe you were following does not do anything until you follow it. Once again, a program on a disk does nothing until it's loaded into memory. Also, if two people are baking the same cake, that is two processes. So two people are baking separate cakes, and they may be at different steps in the same process of steps. There are ways to create a process, or rather there are conditions on which we need to make processes. Operating systems need some way to create a process. In simple systems, all the processes that will ever be needed are all created at startup. With general purpose systems, we, however, need to be able to make processes at any time. So there are four main events in which processes are created: at when the system starts up, when we execute a system call that creates a new process, when the user requests to create a new process, and the last one is for mainframes only, when we start a batch job. So when the operating system is booted, several processes are created. Some for interacting with the user, some that run in the background. These background processes are called daemons or demons. Originally, the term demon did not refer to evil spirits. That is D-A-E-M-O-N. Its earliest use meant something more like guardian angel, which is the reasoning behind calling these background processes demons, or daemons, I guess. When you start your computer, as I said, several processes are created at once. How about when you want to create processes after boot time? Oftentimes, a running process will issue some system call to create more processes. In interactive systems, users can simply start a program by typing a command or double-clicking the icon for a program. Either way, a new process is created to run the selected program. In a command-based system, the new process takes over the window in which it was started. In Windows systems, a started process doesn't have a window, but usually they start with a new window. Initiating a batch job is typical for mainframes, so this means of creating processes is only for batch jobs. Users submit batch jobs to the system, possibly remotely. When the OS decides it has the resources to run another job, it creates a new process and runs the next job from its input queue. So there is a system call for creating new processes. In Unix systems, that system call is called fork. Usually that is accompanied by another system call called execve, which, okay, so when a process calls fork, it creates a child process that is a duplicate of the original process. So these two processes have the same program, but they are two separate instances of the same program. When we call execve, we replace the child's memory image to be that of a different program. So we call fork to create a new process and call execve to replace that child process's code to be that of another program. In Windows systems, that system call is create process, and it actually encompasses the work of both fork and execve. So create process in Windows handles both process creation and loading the correct program into it. In either case, you have a parent child process with distinct address spaces. Any changes made to one does not affect the other. And there are conditions under which a process terminates. Usually it's done its job, or it's encountered an error and needs to exit, or it's encountered a fatal error, or it's killed by another process. So the exit system call in Unix and the exit process system call in Windows, they are called to tell the operating system that a process has finished its work. Sometimes processes encounter an error. If you type in, for example, on Unix systems, GCC, that's a compiler, but you type nothing else, if you just type in GCC by itself, it might say something like no input files given, and it will terminate with an error. Sometimes processes will terminate if you try to do an illegal operation, such as divide by zero. And finally, sometimes you need to kill a process outright. This is typically done, such as, for example, by using Task Manager to end a task. So a process may execute a system call that kills another process. It's called kill in Unix and terminate process in Windows. When a process creates another process, there is a parent-child relationship, and then that child process may create new processes, so we have a sort of family tree. This is called a process hierarchy. Okay, so an example of a process hierarchy can be seen by calling init. After a Unix system boots, a special process called init reads a file telling how many terminals there are. That process calls init. It forks a process for each terminal, and then each process waits for someone to log in. When a user logs in, a login process executes a shell to execute commands, which forks its own process to execute those commands. Windows has no concept of a process hierarchy. There is a special token called a handle that's used to control a child process, but that token can be handed over to other processes, thereby invalidating the hierarchy. Each process is an independent entity, but sometimes processes need to communicate with other processes. Okay, so here is the concept of blocking. There are two ways for a process to be blocked, and both conditions here are different. A blocked process cannot continue because it's waiting for input that's not yet available, or a process can be blocked if the operating system decides it's time for another process to run. So the first kind of blocking is when we are waiting for input. We can't do anything until that input comes in. The other one is when another process is already running on the CPU. Okay, so there are three states talked about in the book where a process is running, it's ready to run, or it's blocked. Other texts and sources may talk about additional states. So in what I call the dinosaur book, which is a different textbook for operating systems. It talks about a created state and a terminated state. Think of created as the beginning of a process's life cycle and terminated as the end of a process's life cycle. I pulled this image off of Wikipedia, and it talks about two other states called swapped, one for waiting and one for blocked. So processes are loaded into memory, and if we don't have enough room for our processes, some of them might be moved to what is called swap space. This is to make room for more processes. That swap space is usually a portion of the hard drive. So the hard drive can be used as an extension of memory. So we swap out processes if we need to make room for other processes. So this can be applied to waiting processes or blocked processes. But we're mainly working with these three states: running, waiting, and blocked here. So a process is, well, I'll call it something else. So running, ready, and blocked. So a process is either running on the CPU right now, a process is either waiting to run on the CPU, it's ready to run, but it can't run just yet. Or a process can be blocked. If it's blocked, it's waiting for something, such as it's waiting for user input, or it's waiting for something else. To implement the process model requires what is called a process table. This is maintained by the operating system. The table has one entry per process. These entries are sometimes called process control blocks, or a PCB. Each entry contains information about the process's state, such as the program counter, stack counter, memory allocation, status of open files, and scheduling information. The specifics of what go into a PCB will vary from system to system, but this table gives you a general idea of what information is needed in a process control block. And this is the steps of an interrupt, by the way. It's one of those concepts that's a little bit tricky to understand, but basically if you are interrupted by something that's higher priority, say you're waiting for a pizza, but you don't want to stand at the front door waiting for the delivery guy to come in. So, the idea behind an interrupt is simple. If the doorbell rings, that's pizza time. However, that interrupt can be used for other events, such as, hey, there's Girl Scouts selling cookies, which may or may not be higher priority than your pizza. That's a simple analogy to how interrupts work. I do have some more detailed information about how a interrupt is serviced here too. Associated with each I/O class is a location somewhere in memory called an interrupt vector, which contains the address of an interrupt service procedure. So this could be so there are basically different interrupt handlers. For example, when someone rings your doorbell, it could be the pizza delivery guy, or it could be Girl Scouts selling Girl Scout cookies. So you would have two different ways to handle those interrupts. And it's not too dissimilar to how a CPU it's not too dissimilar to how a operating system deals with interrupts. Okay? So an interrupt begins by saving the registers of a process in the process control block. Then this information is pushed onto the stack by the interrupt. Then this information pushed onto the stack by the interrupt is removed, and the stack pointer is set to a temporary stack used by the process handler. Yeah, this is one of the more advanced concepts in operating system, the idea of an interrupt. So here are the steps of what happens at the lowest level of the operating system. This is what happens when an interrupt occurs. So the hardware saves the program counter and so on. The hardware loads a new program counter from the interrupt vector. We saves some assembly language procedure saves the registers. An assembly language procedure sets up a new stack. The C interrupt service runs. The scheduler decides which process to run next. The C procedure returns to the assembly code, and assembly language procedure starts up a new process. So a process may be interrupted hundreds of times, maybe thousands of times during its execution, but the point is we start again where we had left off right before the interrupt. When we run multiple programs on a computer, we can better improve CPU utilization. So if the average process competes only 20% of the time, and the other 80% of the time it's doing nothing, then the idea is with 5 processes, we can keep the CPU busy at all times. This actually is not a good assumption. That assumes that none of the processes are waiting for I/O at the same time. So a better way to look at CPU usage is from a probabilistic viewpoint, and here's the calculation for that. So P is the fraction of time that a process is waiting for I/O. We raise that to the power of n, where n is the number of processes. So 1 minus p to the nth power is CPU utilization given p waiting time for I/O and n processes. The degree of multiprogramming is the number of processes a single core CPU can accommodate efficiently. We use this to calculate CPU utilization. So if processes spend 80% of their time waiting for I/O, then we need at least 10 processes to get CPU waste to be below 10%. A more accurate model would be constructed using queuing theory, but the idea is this curve here is an approximation. Queuing theory could produce an even more accurate curve. But again, we can model multiprogramming using this probabilistic model where we have n processes that are waiting for I/O p% of the time. That is, if a process spends 80% of their time waiting for I/O, and we have 10 processes, for example. Okay, so we had left off our discussion on Tuesday, right before we were about to talk about threads. So here's where we get into threads. Your next homework assignment is going to be about threads. So your first programming assignment is going to be programming a simple program that forks into a new process, and then it waits for that process to finish running. Okay, so far we had spoken about processes. A process has a single address space and one thread of control. Oftentimes, it's desirable for processes to have multiple threads, as though each thread was its own process. So, why these threads? Here's why. A program may have multiple things happening at once, and some of those things need to block from time to time. So if we decompose a program into multiple threads that will run in parallel, that makes the programming model simpler. So what makes threads different from processes is the following. Threads that are part of the same process all share the same address space, data, and instructions. Threads are more lightweight, so it's easier to create and destroy threads than it is to create and destroy processes, up to 100 times faster. Excuse me. Okay, so here's what makes processes and threads different. We can speed up. Okay, so we can have different parts of a program be delegated to different threads. So if one thread, for example, on a program is blocked, it can't do anything because, for example, it's waiting for user input. Another thread that is part of the same program can run instead. So this basically makes it so a program is more responsive. And finally, if we have a multi-core CPU, we can run multiple threads at once. Here's the textbook example of what it means to have multiple threads. A word processor has... Consider a word processor that has 3 threads. 1 thread for keyboard input, 1 thread for rendering the document on the screen, and 1 more thread for automatically saving the document. So with only 1 thread, if for example the program is currently saving the document to the disk, then anything that you type on your keyboard won't render onto the screen until the document has finished saving. Also, if the user has made changes at the beginning of a long document, the word processor must reformat the rest of the document as it's displayed on the screen before the user can type again. So if you make changes at the beginning of a long document, you press a button on the keyboard, it's going to take some time for those changes to render on the screen. So even if you type any more after that, it's going to take some time for the program to render all those changes. By having 3 separate threads, you can type away at the keyboard while another thread is in the middle of rendering those changes on the screen. At the same time, another thread could be saving those changes that you make, all without interruption of any other task delegated to each thread. So, yeah. The point is, we can split up these 3 tasks among different threads. This makes the program more responsive. And by the way, it does not work to have 3 processes, because these 3 operations must be done at the same file. And a process, multiple instances of the same program are separate processes. They can't share anything between each other. So this would not work if we did it as 3 different processes. It has to be done as 3 separate threads that are part of the same process. So another useful application for a thread's usefulness is a web server. So a server can have 1 dispatcher thread and several worker threads. When a request comes in, the dispatcher thread chooses a worker thread and hands a request to that worker thread. The worker thread wakes up and checks whether the request can be fulfilled from the cache. If not, it starts a read operation to get the page from the disk. So if this is 1 thread, and if this is 1 thread, it might take some time for that 1 thread to fulfill the task of reading something from the disk. And if another request comes in, that request cannot be serviced until that read operation is done. So it's kind of like a restaurant where you have 1 manager delegating tasks to other workers within the restaurant. That's another analogy for processes versus threads. In this system, the server is written as a collection of sequential threads. So the 2 threads code in this example are infinite loops. The dispatcher thread is an infinite loop of getting requests and handing them to workers. The worker threads consist of accepting requests and retrieving the requested page from a cache, or if it's not in the cache, then from the disk. And considering what requests are coming in constantly from different clients, it would be nightmarish to have this system be single-threaded. Because again, we cannot fulfill another request until we have serviced the previous request. So if this is single-threaded, then you can probably imagine how big the backup of requests can get. So this is one of 3 ways to construct a web server. There are 2 other ways to do that. The second way is have it be a single-threaded system, which basically lowers performance. The third way is to have it be based on a finite state machine. This assumes there are non-blocking system calls. The process is able to work on a different request, but it must save its state before working on a different request. This actually ends up simulating multiple threads, but in a more difficult way. So if we construct the server using multiple threads, we have parallelism and blocking system calls. If we base it on a finite state machine, then we do have parallelism, but we have non-blocking system calls. It's a little bit more complicated, but the idea is, pretend this system is a restaurant with a manager and several workers. The manager delegates tasks to each of the workers instead of one manager doing everything in the same restaurant. So now that we hopefully have a good idea of how threads are useful, let's look at them more closely. So the process model is based on two independent concepts: resource grouping and execution. Sometimes it's useful to separate them, and this is where threads come in. So one way to look at a process is by grouping related resources together. So a process has an address space that contains text and data and other resources such as child threads, open files, and so on. So we can put these together as one process. This makes managing these resources easier. The other concept is to look at a process as a thread of execution, or simply a thread. A thread has a program counter, a register, several registers actually, and a stack. In this way, processes are used to group resources, whereas threads are the entities scheduled for CPU execution. Threads allow for multiple executions to take place within the same process, or within the same process environment, to a large degree independent of one another. So having multiple threads run in parallel is like having multiple processes run in parallel, except threads that are part of the same program all share the same resources as that one program. So a process can be broken up into multiple threads when it is they all share all the same resources allocated to that one process. And it's because of this, threads are sometimes called lightweight processes, and the ability to run multiple threads in the same process is called multi-threading. So the classical thread model, here, this diagram shows 3 threads across 3 processes versus one process with 3 threads. On the left, each process has a separate address space with a single thread of control. In B, on the right, there's only one process with 3 threads of control. The key difference is that in A, each thread has its own address space, but in B, we have 3 threads that can all access the same address space. On a single core system, each thread takes these 3 threads take turns running on the CPU, much like how switching between processes gives the illusion of multiple processes running at once. The same is true for threads. So much like how we can switch between processes really quick, we can switch between threads really quick too. Give me a minute. Sometimes I'm interrupted by a ding that is from my email, and I have to stop what I'm doing to read the email. Sometimes it's important, sometimes it isn't. Interrupts all over again, okay? But my point is this. The CPU can run multiple processes by running one process at a time, but switching to a different process really quick. So each process is run for a few tens of milliseconds until the CPU runs a different process. The same is true for threads. So if we have multiple threads that are part of the same process, then if a task delegated to a thread is blocked, we can run some other part of the same program. This makes the program more responsive. This is why we want to write multi-threaded programs, so we can delegate different tasks to different threads. So even if one part of a program is blocked, say it's waiting for user input, the other parts can still run. When we have multiple processes loaded into memory, we actually need to protect them so one process doesn't overwrite the memory of another process. This kind of protection does not exist between threads. Not only is it impossible, it's not necessary. So threads are owned by a single user and are made with the intent that they cooperate with one another, not fight one another. Threads therefore must be able to share resources with one another. Though there are some things about a thread that is unique to each thread. So, at the process level, a process has its own address space, it has its own global variables, it has its own list of opened files, it has its own child processes, and so on and so forth. At the thread level, each thread has its own program counter, it has its own registers, it has its own stack. It also has its own state, so blocked or running, for example. Threads share the memory. Threads share the same memory. If we have three processes that are part of the same program, they all share the same memory. They all can share all the same resources as that one process. Processes cannot share resources the same way threads can share the same resources. Keep in mind that processes are a unit of resource. Keep in mind that processes are a unit of resource management, not threads. Items under per process items are things that threads share. Items under per thread items are unique to that thread and cannot be shared. So each thread is its own thread of execution. So the sequence of steps that a thread will follow is unique to that thread. But they can still share files, they can still share memory. Processes cannot easily share things between one another. It's important to realize that each thread has its own stack. Each thread will generally call different procedures, so their execution histories will be different between one another. One thing we can do with p-threads, and I guess we'll have p-threads to be our next assignment, each thread we can give a different function for each thread to run, and then each thread will do something else from one another. So here's the classical thread model. When multi-threading is available, a process usually starts with one thread. When we call some function, let me back up. If we have multi-threading available, a process usually starts with one thread, and there is some system call that we can call to create another thread. It's not necessary or possible to specify anything about this thread's address space, since it shares it with the thread that created it. So when a process creates a new thread, those two threads share the same address space. As part of this call to create a new thread, the name of a procedure can be passed to it. That basically tells that thread what to do. And sometimes threads are hierarchical. These are parent-child relationships. But it's often not the case because all threads are basically equal. In any case, this procedure returns some sort of thread identifier, a thread ID if you will. When a thread has finished its work, it exits by calling another library procedure such as thread exit. Some systems can have threads wait for other threads to exit using something like thread join. This blocks the calling thread until a specific thread has exited. It's much like the process creation and termination, but with approximately same results. Another common thread call is thread yield, which allows a thread to voluntarily give up the CPU, allowing another thread to run. This is important because the mechanisms that enforce one process to run at a time and decide whether it's time for another process to run, that mechanism does not exist at the level of threads. As useful as threads are, they can throw in some complications to the programming model. So the fork system call, for example, when a process calls fork, it creates another process that is the same program as the running process, but a separate instance. If the parent process has multiple threads, does the child process have any of those threads? What happens if a thread in the parent was blocked on a read call? Is there a blocked thread in both the parent and the child? When we type in a line, does the parent get it, or the child get it, or do both get it? The same problem exists with open network connections. And there's more. What happens if a thread closes a file that another thread was reading? What happens when a thread notices there isn't enough memory, starts to allocate some more memory, and it switches for a different thread? Will that new thread try to allocate more memory? And if it does, it'll result in twice as much memory than we needed being allocated. Solving these problems requires some careful thought and design to ensure multi-threaded programs run properly. So here is where our discussion on pthreads begins. So I give this out as your next assignment because we haven't finished up our assignment on processes just yet. So POSIX threads, or as it's called short, pthreads. So there are a few system calls that we'll see here. The first one is pthread create. Oh, by the way, there are about 60 different function calls related to the creation and operation of threads. We're only going to talk about 6 of them here. All pthreads have an identifier, a set of registers, and a set of attributes. We create a thread by calling pthread create. This returns the thread ID of a newly created thread. In CSE-4600, I call this a thread handle. It's analogous to the fork system call, but there is no accompanying exec call. So there is no such thing as exec VE at the level of threads, because everything that is available to a process is all available to every thread we create. So once a thread has finished its work, we call pthread exit to terminate that thread. This takes in a thread ID, or I call it a thread handle, to specify which thread should exit. Sometimes a thread must wait for another thread to finish its work and exit before continuing. We do this using pthread join, where we pass in the thread handle for a thread, and the main thread waits for that. Okay, so if a thread calls pthread join, it's basically waiting for another thread that was created previously to finish its work, so it'll join back with the main thread. Usually, we talk about the fork and join model. So the main thread creates one or more child threads, and then the main thread calls join for each thread created this way. So the main thread waits for its child threads to finish their work and join back with the main thread. As mentioned, there are no built-in automatic mechanisms to signal when threads should be switched for other threads on the CPU. It is up to the programmer to provide this signaling. And this is done with pthread yield. Each pthread has attributes associated with it, and those are created using pthread attribute init. This creates and initializes a thread's attribute structure. Pthread attribute destroys those attributes. This frees up memory. It doesn't affect the threads using it. So here's an example thread where we have a hello world program that's multi-threaded. So this is a simple hello world program that uses pthreads. So if you're also taking 5250, this is a little bit different from the one that's shown in 5250. Basically, it's the same thing as the one in 5250. We have one main thread create multiple threads, and to each thread we pass it a hello world function. So each thread says hello world, and then after that the threads join back with the main thread. Okay? Though this one's a little bit different, it's just the call for pthread create. There isn't a corresponding pthread join. So, in the 5250 material, I talk about having a pthread join for every accompanying. Okay, so in CSE-5250, I talk about having pthread join for every call to pthread create. So how do we implement threads? Well, there are two ways to implement threads in the operating system. We can have them be in the user space, or we can implement threads in the user space, or we can implement threads in the kernel space. And there is a third hybrid method to implementing threads. So the first implementation is to put threads in user space. So the kernel knows nothing about these threads. As far as the kernel is concerned, it is managing ordinary single-threaded processes. The advantages to implementing threads in user space is this. A user-level thread package can be supported on an operating system that normally would not support threads. In the past, all operating systems were like this. Threads were implemented using a library. Each process can have its own customized scheduling algorithm. More on this later. So this is the diagram on the left here. So threads run on top of a runtime system, which is a collection of thread-related procedures. When threads are managed in user space, each process needs a thread table analogous to the kernel's process table. This only keeps track of the per process thread properties. If a thread is moved from the ready state to a blocked state, the information needed to restart as a thread is stored in the thread table. When a thread does something that causes it to be blocked, and that's another interrupt, give me a minute. That was my alarm clock, don't worry about it. When a thread does something that causes it to be blocked locally, it calls a runtime system procedure that checks which threads must be put in a blocked state. If there are threads to be blocked, it stores the blocked threads registers into the thread table, looks for another thread that's ready to run in that table, and reloads that thread registers from that table. As I mentioned earlier, it's easier to switch between threads than it is to switch between processes. And this is why there's just less stuff to load and unload. The one key difference between processes and threads is this. When a thread is finished running and calls thread yield, that thread's information is saved in the thread table. The thread scheduler is then called to select another thread to run. With processes, we need to trap to the OS to signal that a context switch should be carried out. This requires, among other things, unloading the process from memory and saving its state. With threads, no such trap is necessary. It's a local procedure call. So this is what makes switching between threads easier compared to switching between processes. With processes, we need to tell the OS we need to switch between processes. That is what's meant by trap to the OS here. We're signaling to the OS that it's time to switch from one process to another process. And then we have to save the process's state. With threads, we don't need to do that. There's just less stuff to switch, basically. So there are some problems with user space threads. How are blocking system calls implemented? If a thread performs a blocking system call, it blocks all other threads in that process. So this can be resolved by having what are called non-blocking system calls, but it requires changes to the operating system itself. An alternative solution is to tell in advance if a call would block. This exists in most Unix system calls as the select system call. That tells the caller to tell whether a read system call will block. If the call will block, the call is not made and another thread is run. The next time the runtime system gets in control, it checks again whether it's safe to read again. This just requires system call rewrites, system call library rewrites. So how does the system handle what are called page faults? We'll talk about page faults in Chapter 3, but it is a means of running programs without having... So page faults exist because when we load a program into memory, we don't need to load the whole program into memory. We only need to load the parts that we need. So when a page fault occurs, that's because there was something that we needed to read from memory that wasn't loaded into memory. So that is a page fault. If a program needs to access part of a program that isn't loaded into memory, that is a page fault. If a thread causes a page fault, it might block all other threads, even if all those other threads are still able to run. So we might have 3 threads that are doing something on their own. One thread needs to access something that isn't loaded into memory. If those 2 other threads don't need to access, if those 2 other threads are able to run, to block them would be unproductive. So, I guess here is my analogy for multi-threading. Imagine you are building a Lego train set. Here's the train. A process is the step-by-step action of building the train brick by brick, car by car. And depending on the set, there might be other train-related accessories such as a train station or cars or storage containers that would be loaded onto the train, though this is a passenger train, so I guess there would be other cars that would be part of the train. You can build the train by yourself, but it goes faster to have some helping hands. Multi-threading is where you have your friends help out with building your train by each building a different car in the same train. Building a train car does not affect the act of building the next car. So the idea is we can build this train, we can build up the train cars in any order. Paging is where, okay, so paging is a little bit weird in this context of building a train car. If you have the instruction booklet for building the train divided into smaller booklets, paging would be if you could only have one instruction booklet on the table at a time. So instead of having all the individual booklets on the table, you would only have one at a time, or probably better, you would only have the booklets on the table that you need. So there might be individual instruction booklets for building different train cars on your train. A page fault would be like finding a manual that wasn't on the table. Ideally, looking for that missing manual should not stop everyone else from building their train cars. So that is my analogy for multi-threading. Multi-threading is, okay, so a process is basically like building a Lego train. Multi-threading is when you get your friends to help out with building other trains in that train set. A page fault is what happens if you had to look up one of the manuals for building one of the train cars because it wasn't on the table. This should not stop everyone else from building their train cars, however. Okay, so now we're going to talk about implementing threads in kernel space. No runtime system is needed here. Instead, give me a minute. No runtime system is needed for threads in kernel space, and there isn't a thread table in each process. Rather, the kernel has that thread table. When a thread wants to create a new thread or destroy a existing thread, it makes a kernel call which does that for that thread, and then it updates that thread table. So, for user level threads, each process had its own thread table. For kernel level threads, the kernel has a thread table for all threads in the whole system. The thread table in the kernel holds each thread's registers, state, and other info. So it's all the same information with the last section where each process had its own thread table, except it's the kernel that has information for every thread in the whole system, even for threads between different processes on unrelated processes. As normal, the kernel maintains a process table. So the kernel maintains a process table and a thread table. So the kernel is managing threads, even if they are threads from different processes. It's a little bit weird. All calls that might block a thread are implemented as system calls. This comes at the higher cost compared to having a runtime system procedure. When a thread blocks, the kernel can either run a different thread from the same process or a different thread from a different process, depending on what's ready to run. With user-level threads, the runtime system keeps running threads within one process until the kernel takes away the CPU from the process or there are no more threads to run. So, for user-level threads, the runtime system determines whether there is a thread ready to run. Is this thread ready to run? No? Okay, let's run this thread. Is this thread ready to run? No? Okay, let's run this thread. Is this thread ready to run? Oh yeah. Yeah, we can run that thread until that thread stops running, or the CPU scheduler decides it's time to run this process instead. Is this thread ready to run? Yes, let's run that one. Give me a minute. Okay, so when a thread blocks, the kernel must decide whether to run another thread on the same process or another thread from a different process. So is this thread ready to run? No? Let's try this thread. No, it can't run? Okay, let's try this thread. Okay, maybe that thread isn't ready to run either. Let's try running a thread from a different process. So maybe it's this thread that's ready to run instead. Due to the higher cost of creating and destroying threads in the kernel, some systems will actually recycle threads instead. So it's kind of similar to a concept in game programming called object pooling, where we don't create and destroy the same game object over and over again. We just save it until we're ready to use it again. We don't destroy threads here. We instead mark them as not runnable, and its kernel data structures are not affected. When a new thread is needed, we just activate one of those not runnable threads and reactivate it. Thread recycling saves the system the overhead of having to create and destroy threads. Kernel threads don't require any new non-blocking system calls. If a thread causes a page fault, the kernel checks whether there are any more runnable threads as part of that process. If so, one of those threads is run as the missing page is paged in. So let's say these three threads are part of the same process. One thread does something that results in a page fault, and this thread is blocked from running because it's trying to access something from a page that isn't loaded into memory. Meanwhile, we can run these two other threads because, well, they're able to run still. Unless one of these two pages causes another page fault, of course. So if this thread here causes a page fault, it stops running until we're able to run until we're able to run it again, because we have to load that missing page from memory. Meanwhile, we can try running some of the other threads in the meantime. So implementing threads in kernel space solves many of the issues with having user-level threads, but not all of them. So what happens, for example, when a multi-threaded process forks? Does the forked process get only one thread, or does it get as many threads as the calling process? The answer to that depends on what happens next. If a forked process calls exec, then it should only have one thread. If, however, the forked process continues to execute, it may be better to reproduce all threads. And there's also the issue of signals. In the classic process model, the signals are sent to threads. If there are multiple threads, to which thread does the signal go? Or rather, which thread handles that signal? Again, this depends on whether there's only one thread to handle the signal or multiple threads to handle that signal. So this leads up to the hybrid implementation, where one kernel thread may be multiplexed between multiple user threads. The programmer can determine how many kernel threads to use and how many user-level threads to map to each one. The kernel is only aware of the kernel-level threads and schedules those. If multiple user threads are mapped onto one kernel thread, then they take turns using that kernel thread. Although kernel threads are still better than user-level threads in many ways, they are still slower, and researchers have investigated ways to do that. And one such method is called schedule activations. So the goal is to mimic the functionality of kernel threads, but with the performance and flexibility that user threads have. So this is Anderson et al. And includes related work by Edler et al. And Skedwer. So schedule activations. This was an approach devised by Anderson et al. With related work by Edler et al. And Scott et al. The goal, as I mentioned, is to mimic the functionality of kernel threads, but with the performance and flexibility of user threads. User threads shouldn't have to make non-blocking system calls or check whether a system call has a block. Basically, if a thread blocks, it should not block all other threads. In other words, if a thread blocks, we should be able to run another thread if there is another thread to run. Efficiency is achieved by avoiding unnecessary transitions between user and kernel space. If a thread blocks waiting for another thread to do something, there is no reason to invoke the kernel. This saves on overhead, thereby increasing performance. The user space runtime system can block the synchronizing thread and schedule a new one by itself. When scheduler activations are used, the kernel assigns a certain number of virtual processors to each thread and lets the user space runtime system allocate threads to these processors. This can also apply to a system with multiple CPU cores. Initially, a process has only one virtual CPU allocated to it. The process can request more and return them when it's done. The kernel can also take back virtual CPUs if there are other processes that need them. When the kernel knows that a thread is blocked, the kernel notifies the process's runtime system by passing to the stack the number of the thread and a description of the event that has occurred. This notification happens by having the kernel activate this runtime system at a known address. This is called an upcall. Once activated, the runtime system can reschedule threads. This typically happens by marking the current thread as blocked and restarting another thread that's ready to run from a list of threads that are all ready to run. When the kernel learns that the original thread is ready to run again, it makes another upcall. The runtime system can either restart that thread or put it on that list of threads to run later. When a hardware interrupt occurs while a user thread is running, the interrupted CPU switches to kernel mode. If the process isn't interested in the interrupt, it puts the interrupted thread back to the state it was before that interrupt. If the process is interested in the interrupted thread is instead suspended. The runtime system started on the virtual CPU with the state of the interrupted thread on the stack. What thread to run next is up to the runtime system to decide. It can run the interrupted thread again or do something else. The one objection to upcalls is that it violates the inherent structure of a layered system. In a layered system, a layer offers services to the next layer, but it cannot call any procedures in the next layer. Upcalls don't do that here. Threads are frequently used in distributed systems. Distributed systems are computers that are linked together by a network. In a distributed system, messages are sent between computers and a means of handling them is needed, usually by having a process or thread that is blocked on a received system call. So it's waiting for an incoming message. When a message does arrive, the process accepts it, unpacks it, examines the contents, and then processes that message. A different system is also possible, and this is called a pop-up thread. So when a message arrives, it causes the system to create a new thread to handle the message. Since this is a newly created thread, it doesn't have a previous state to restore. It's a whole new thread. This speeds up making the thread and reduces the latency between message arrival and processing the message. So, for pop-up threads, this requires some advanced planning. In which process is the thread run? If the pop-up thread is a kernel space thread, creating the thread becomes much faster compared to making a user space thread. However, the kernel is buggy, there's no way to preempt it and the message may be lost. So section 2.2.9 is a discussion on how to make single-threaded code multi-threaded, and it's basically tricky. So I'm gonna leave it to you to read this section on your own. It talks about the pitfalls of making single-threaded code multi-threaded, such as how do you deal with global variables? How do you deal with library procedures with non-reentrant code? Basically, how does a library handle a second procedure call when it's not done with a previous one? Also, how to deal with the memory allocation, how to handle signals that are not thread specific, and how to manage the stack. So yeah, that is everything that I wanted to talk about for our discussion on threads. I'm gonna have a next video discussing what we're gonna be doing for our first lab. That is a simple hello world program with one process forking into multiple processes. So stay tuned for that next video, and I'll leave it there for now. Our next assignment, we're gonna try writing a multi-threaded hello world program. Okay? Alright. I'll see you in the next video. Bye.